Good day, guys. We have to look at another problem for partial differentiation from pattern 6. So this one says, given that z is the ln of 2x minus 3y, we need to calculate the following. So we need the second partial derivative with respect to x as well as with respect to y. So we can go now for the first one. If I need the second derivative, obviously I start with the first. So I'll get the first derivative with respect to x. So this tells me that I have to differentiate this with respect to x. I'm looking at this is a function of a function. So when I differentiate ln, it gives me 1 on 2x minus 3y. That's what ln will always give you. Then you have to go in now and search for x to differentiate. So if I go in, try to differentiate x, the first one will give me 2, the derivative of 2x, but the second will give me 0 because there is no x appearing there. So if I simplify this, this should give me 2 into 2x minus 3y to the power negative 1. I'm just bringing it up because I don't want to use the quotient rule. I rather prefer to put it up so that it becomes the chain rule when I'm doing the second derivative. You can also leave it down as 2 over 2 minus 2x. Some other person can still see it as 2 on 2x minus 3y and use the quotient rule. So I prefer the chain rule. For me, it will work faster. I hope it helps you that way also. So we go now to the second derivative with respect to x. The second derivative means I'm redifferentiating this with respect to x. So we know the 2 there is a constant. We don't have to bother it. All we need to do is to differentiate this function as a function of a function. If I differentiate this, the power comes in front, so it becomes negative 1. I capture 2x minus 3y. Then I subtract 1 from the power. It gives me negative 2. Then I go inside the core function and look for x and differentiate. So if I'm differentiating, it means I'll get 2 from differentiating 2x. If I differentiate the other one, it must give me a 0 because there is no x. So don't make a mistake to say we'll give you a 3. We are differentiating x, not y. So from here, you will see that what you have here is negative 2 multiplied by 1 on 2x minus 3y to the power 2, then times 2. So those ones will give us negative 4 on 2x minus 3y, all that square. So that is our second derivative of that function with respect to x. So we can now look at the b part, which is repeating the same problem with respect to y. So to differentiate with respect to y, we will capture our function again, which is 2x minus 3y. If I need the second derivative, I must start with the first derivative with respect to y. To y means I will do my chain rule again. When you differentiate ln, it gives you 1 on 2x minus 3y. Then you go inside the core function and differentiate 2x minus 3y with respect to y. So now you are looking for y. So if you differentiate the first term, you get 0. You differentiate the second, you get a 3. So again, I would prefer to capture this as negative 3. Then I bring the 2x minus 3y up as 2x minus 3y to the power negative 1. So I can now go on and look for my second derivative of that function with respect to y. So even though it looks like a product, because this does not contain y, you capture it the way it is, then you start differentiating it by the chain rule. So if I use the chain rule here, I'll multiply the power in front, which is negative 1, then I capture 2x minus 3y, I subtract 1 from the power, it becomes negative 2, then I go inside now, I search for y and differentiate, which means the first term there will give me a 0 because there is no y. If I differentiate the second, I get 3. The derivative of 3y is a 3. So here, you've got a negative 3 here and a positive 3 here, which if you multiply them, they will give you a negative 9. Negative denominator, that's 2x minus 3y, all this square. So guys, that's how easy it is to handle problems with log. So let's now see how to handle an exponential problem. This one says we should do a proof and prove that this second derivative is the same as that second derivative. The only difference is that with this, you start by differentiating x, you end with y. Here you start with y, we end with x. So this time we have our exponential function x e to the power y, x over y, which can also capture it as e to the power x times y to the power negative 1. So I intend to do the left hand side first. That means I will differentiate with respect to x first, and then the second derivative with respect to y. So my first derivative with respect to x means I'm differentiating this function. When you differentiate e, it always remains as e first, but this is a function of a function. When I go to the core function, I target on the x. When I differentiate x there, it gives me a 1, then I'm not supposed to touch that because it is not x, so I can call it 1 over y. So it means my answer for this one is 1 over y e to the power x over y. So that is what I get, which can also be captured as a fraction. So let me rather capture it as a fraction, e to the power x over y divided by 1. So that way, I'm now going to the second derivative. And what am I doing here? I'm now differentiating the answer of the first derivative with respect to y. So y is now the active variable. And when you look at your problem, y finds itself at the numerator and at the denominator. So that therefore means this is quotient rule, because the active variable that we're looking for is at the numerator and at the denominator. So here we need to be using v u prime minus u v prime on v squared. That is how we are going to see our problem. So we'll go through that problem and differentiate y. So the denominator is the easy part, because you need v squared and your v is y. So I'll get my y squared. And the numerator, I will take v, my v again is y. Then I will differentiate e with respect to y. So this e here is the same thing as the e you see there. If you have to differentiate it with respect to y, each time you differentiate e, it must stay the same first. That is your chain rule. Then when you go to the exponent, you are now targeting y. So it means your x will be written exactly the way you see it. Then to differentiate y, you bring down the power, then you subtract 1 from the power, it becomes y to the power minus 2. So that is just v u prime. Then I'll take minus u v prime. My u is e to the power x over y. V prime means I differentiate v, which is a y, that gives me 1. So if you try to simplify it, you see that at the numerator I have y e to the power x over y times x times negative. I will put negative in front there. Then I get 1 over y squared, 1 over y squared minus e to the power x over y. So that this y can take care of 1 of that. So it means I'm actually having negative e to the power x over y. Sorry, negative x on y. So I have negative x on y. E to the power x over y minus e to the power x over y. Then divide by y squared. So that is my left hand side. If I got it right, there is a negative here. Let me not forget, there is this negative, then there is this x over y, because this y reduces that one, then there is e there. So that's what I'm getting. So I want to prove that the right hand side is exactly the same thing. So with the right hand side, I capture my z as before, e to the power x over y, or e to the power x times y to the power negative 1. So I differentiate with respect to y first. So if I'm differentiating z with respect to y, you differentiate e, it will stay the same first. Then you go to the exponent and differentiate y. That means at the exponent x will stay the same. Then if I differentiate y and bring the power in front, it becomes negative y to the power negative 2, which if I simplify this will be giving me negative x e to the power x over y divided by y squared. So that is what I have. And I can now go on and then look for the second derivative with respect to y and with respect to x. So this is where it becomes interesting. In the second derivative, you are differentiating the first derivative with respect to x because we are already done with y. So if we are doing that, it means looking at our problem, we don't have to touch the denominator. The denominator is already taken care of. So let me not say it's taken care of. It doesn't have x. X is what we are targeting. There is no x there, so there is no need differentiating the denominator. So our target is just the numerator, and that numerator has a negative. I can put it out as a constant, and then apply my product rule here. So this will be a product in terms of x, because each of them has x. So if I'm to differentiate that using my product rule, I will need u v prime plus v u prime. So I have to go through that. My u is an x, v prime means I'm differentiating e. It will stay as e to the power x over y, but don't forget to go to the exponent, which is the same exponent there. Now you search only for x to differentiate. So in this exponent, if I differentiate only x, that will give me 1 over y, because I have x over y, I'm only differentiating x. So I've succeeded to do u v prime. I'll then add v u prime. My v is e to the power x over y, then my u is x. If I differentiate x with respect to x, it gives me 1. So if I now open up my bracket, the negative will go through. I'll be getting negative x over y. If I bring these two together, e to the power x over y, then minus e to the power x over y divided by y squared. If you look at the answer here and look at the answer there, you see that they are exactly the same. So therefore, we have succeeded to prove that the partial derivative with respect to xy is the same thing as the second partial derivative of z with respect to yx. So guys, this is how partial differentiation is supposed to be done. Thank you very much.